Hello, hello. Welcome, one and all. Just getting set up here with the Camb.ai team. I think Matt, I believe, is here from Camb.ai. You could just uh, get get that speak on stage up there. There he is. Hey,
Hello, can you hear me?
welcome, welcome. We can. Thank you so much for coming in.
Oh,
So
no, thanks for having us.
yeah, I'll just do a quick my quick spiel here at the top. I'm gonna be recording the session for us, and then we'll get to talk more about Mars 5 here.
Oh,
So
no, sure, thanks.
So yes, these are our member organized talks, AMAs, demos, and discussions. They're all about sparking new ideas, sharing your open source projects, finding collaborators, getting to know one each other better in the Mozilla AI community here. My name is Matt Cool, aka Maita, Mozilla community manager here in the server, and I wanted to warmly welcome all those who've gathered here and those listening post event. I believe we're streaming with Camb.ai. Is that correct, Matt?
Yeah, I think we're streaming to our YouTube channel. Just in the audience here, Arnav and Peter, they're also from the Camb.ai team.
Ah, beautiful. Great. Yeah. So if we can get that link, we'll get that link in chat here in a second. And then today, if you have a topic you're passionate about or a project you'd like to share generally, if you'd like to ask a question for our presenters, you're welcome to join the stage with us whenever our host is ready. Just hit request to speak, and our mods will bring you up on stage. It'll take a few seconds, but we'll get you up there. So if you encounter any issues here, let me know in the chat, and I'll see what I can do to help resolve. But without further ado, here's Matt from Camb.ai.
Cool. All right, so thanks everyone. And yeah, what I really had in mind is I'll just give a quick talk of just how Mars is, what Mars is and how it works, and then we can move on to just general discussion or any other questions you might have for us or on plans for Mars and yeah, just general collaboration ideas. So yeah, let me just see if I can share this. Uh, I think everyone can. Um, if you cannot see, just let me know. But yeah, so this won't be too long. I'll just essentially just give a more detailed overview, technical overview of how Mars works. So essentially what it is, it's a text-to-speech engine, right? Um, and ultimately, it's one of these two-stage text-to-speech models. So recently in text-to-speech, there's been this increasing trend of trying to scale up a lot of the old models and almost simplify them to make them a bit like more like the language models that we've seen do so well in the last few years. And typically, what a lot of them do recently is to separate the concerns of text to speech into two separate problems. The first one is to generate linguistic content, generate the actual base kind of sounds that are to be spoken, like generate the very coarse level sounds to be spoken. And the second part is to generate essentially higher frequency details, fill in all the nuance and high frequency information in speech, all the things which are kind of not super coarse, low level linguistic features. Um, and our Mars 5 model that we've now made follows a similar process. We've got two models. The first is an autoregressive model that looks like a language model, and the second thing is a non-autoregressive diffusion model that effectively, and what the autoregressive model does is it tries to, again, produce the coarse speech features, the kind of raw sounds being said, the low quality, but what words are being said, while the diffusion model attempts to kind of refine these coarse features to make them sound more high fidelity. But this is kind of high level, so ultimately each of these models, you feed in the text you want to synthesize and the speaker you want to the reference speaker you want the voice to inherit from, and then it'll produce output speech ultimately. But this is pretty high level, so let's get a bit more, concrete about how things actually work. So let's start with the autoregressive component, this big transformer here. And what it's responsible for doing is producing these low-level speech features that kind of correspond to the words being said. So ultimately, it's going to be a decoder-only transformer, a standard Mistral-style transformer. And so it's going to take in a sequence of tokens and spit out a sequence of vectors corresponding to predictions of the next token. Um, and how it works is that we take some transcripts that we want to be said, append a beginning of sequence, end of sequence to it, and then encode it with byte pair encoding to compress it a bit. This gives us a simple input sequence. But then, of course, together with this, we want to actually append some speech features. But then the question arises: how do we get audio into a nice sequence of discrete tokens corresponding to coarse things? Um, what and how we attempted to solve that is to actually use encodec. So ultimately, what happens is that we have our waveform here, and then we feed it through encodec, and this converts it to a sequence of discrete vectors, or vectors of discrete tokens, in essentially several different code books in a discrete codec. And what we do, since we only interested in the AR part with the coarsest, most rough level speech features corresponding to the words being said, is we just take the L0 codes, the first code book, lowest level codes, because this is a residual quantizer. So the first level corresponds to the most coarse speech features. Then we simply byte pair encode that with the byte pair encoding trained on these coarse speech features. And this gives us a bunch of other tokens that form the rest of our input to our transformer. So now we've got essentially, our input to our transformer has two parts: the tokens corresponding to text and the tokens corresponding to speech. And the outputs are simply the text outputs correspond to the text positions and the output corresponding to the speech positions. And at each time, it's just predicting the next one. This text token is predicting this text token. This text token is predicting what this one should be, and we can simply train that with a standard cross entropy loss in a next token prediction problem. Of course, we weight the positions for the speech outputs more, because at inference time, we only actually going to sample the speech. We're not sampling new text outputs. We're not actually using this as a language model. So now the big question you might ask here, or the big problem here, is that where is this model actually getting the speaker identity from? If we look at this last text token here, this last this will correspond to the end of sequence token, right? And then it's predicting now what should the first speech token look like. How should it know what the speaker is of that? Because this transform is causal. These autoregressive models, they're always causal. So this actually has no information from these prior tokens on what the speaker should be. So we need some way to specify speaker information to this model. So what we actually do is we modify this base picture a little bit and do something a little bit like this. So in addition to the text tokens, we add a token before it. And this token we want to represent the speaker identity, including the emotion and other possible things. In other words, some sort of prosody combined with speaker embedding that the model can use to figure out what should these first few speech tokens look like. And how we obtain this is in a fully end-to-end fashion, whereby this reference audio during training, instead of just taking the coarsest book codec and feeding them in as input here, we actually feed all the code books. So this is a sequence of 8 discrete numbers for every about 20 or 16 milliseconds. And we feed that into a small encoder-only transformer with a special classification embedding at the front, a special speaker embedding learnable position at the front. And then we just take this first position's output vector and use this as the speaker embedding, and an implicit speaker embedding. There is no explicit speaker embedding loss. There is no explicit training this model to be a speaker embedding model. But since this is an autoregressive model, the actual only way it can obtain the speaker information for this first speech position here is through this. And yeah, essentially, this kind of forces it to be a nice speaker embedding model. And if you do some evaluations, it seems to not be too bad as a pure speaker embedding after doing some normalization. And yeah, that's generally how the AR model works. So now let's talk a bit about the non-autoregressive model. And this is a diffusion model. Yeah, sorry. And this is a diffusion model. And essentially, how it works is a bit more complicated, but nothing's too crazy. And the heart of it is a transformer, an encoder, decoder, standard full transformer. And essentially, the input sequence to our encoder is going to be a bunch of text features and a speaker embedding. And then our decoder is going to have a bunch of these discrete encodec features as input. And it's going to then output also these discrete encodec features. But more in detail, like with the AR model, we've got our text and we apply byte pair encoding to compress it a bit. We've got our reference speech that we again encode with this encodec into a sequence of discrete vectors, uh, feed this through our encoder-only transformer, take the first output, and use this as an implicit speaker embedding. Um, and then, of course, since this is a diffusion model, we just append the time step, add the time step to all these vectors here to condition the model on the current time step. And now, I guess it's a bit confusing exactly how these diffusion models work, but ultimately, this is trained as a standard DDPM, denoising diffusion probabilistic model, um, but as a multinomial diffusion. And the reason why is that these inputs, each of these inputs from this encodec are discrete vectors. Well, they're 8 code books, they're 8 discrete numbers every 16 to 20 milliseconds, somewhere around there. So essentially, we're trying to denoise a sequence of discrete numbers or vectors. Yes, we want to ultimately denoise all these discrete numbers. So we're not operating in the continuous domain. So we use a multinomial diffusion approach. And to give you an idea of what this looks like, here's a figure from a paper in 2022 to kind of give you a flavor for how multinomial diffusion works. So normally diffusion, you've got some number of time steps, in this case 200 time steps. This is from a speech recognition problem where we're training the model to predict Mr. Quilter. That's the ground truth, right? From some audio, we want to predict Mr. Quilter. And then how you'll initialize this model, during inference time is that these inputs here will be completely random noise. And for us, noise means we're going to sample a random digit, a random entry in this encodec codebook. And then, at each inference time, we're going to pass it through the model, predict what the next, time step in the denoising reverse diffusion process should be. And each time it'll slowly denoise it until the output discrete, the discrete outputs actually look like this encodec, the correct encodec values. And to give an idea, a bit more exactly how this works at inference time, here's the picture from before. And what does this actual input look like? And it's going to be some sequence length by the number of codebooks. And for encodec, this is 8. So it's going to be a tensor of 8 tall and however long the audio is. And if we've got some reference audio, what we can actually do to improve the quality a bit is fix all the speech codes corresponding to the reference audio, those positions. And then, of course, fix all the tokens corresponding to the autoregressive model. Since autoregressive model is going to predict the L0 codes, and we need to then fill in all these high fidelity codebook things. And remember, each of these little vectors here will look something like this. It'll be 8 numbers, all discrete between 0 and 1 or 2, 4, because that's how many entries there are in encodec's codebooks. And this one will be fixed by the autoregressive model or during training by the ground truth audio. And the rest of these are actually going to be slightly denoised, possibly flipped to a different value at every different diffusion time step. And of course, these are fixed from the reference, by the reference audio, whatever that is. All 8 codebook entries here are fixed since we know the audio. And yeah, this is trained with just a fairly standard DDPM loss. And by the end, it means we've got this nice model that can, given the first codebook entry, the text, and the reference speech, actually produce a pretty good prediction for what these other codebook entries should be. And that's the high level of how these two models work. But now, one thing I would like to also chat about is this idea of deep versus shallow cloning that we talk about a bit with the model. And how this works essentially is that we kind of provide 2 ways to do inference. Given the way that we've trained this, and I've explained these 2 different ways, there's actually 2 ways to do inference. The first way is a shallow clone. And If we just look at the autoregressive transformer from the AR model, and we ignore all the pre-processing steps that happen down here with the EM codec and the BPE and, the speaker embedding transform. We ignore all of that, and we just look at the actual transformer input and output. A shallow clone looks a bit like this. You have your reference audio, you get your implicit speaker embedding by passing through the small transformer. Then you simply take your text that you want to synthesize, and then this is, some sequence of tokens. You have your end of sequence token here, and then you simply, pass it through the model, get the first speech output, sample from it, use that as the next one, get the output, sample from it, auto-regressively, predict the next speech token until you predict the end of speech token, and then you stop, right? So this is fairly simple. There's not really any, there's not much wasted computation here. We're not doing inference calls where we shouldn't. The input sequence is, reasonably short already. So this is nice and fast. But the main problem here is that, we don't get, all the reference speaker information, its prosody and everything is kind of compressed into one vector. So it doesn't have the best or the most detailed information of how the reference speech works, of how it should say the output given the reference speech. So what we offer as an alternative to this, that's slower but higher quality, is a deep clone. And essentially, all that we're doing is we're adding these two sequences in our outputs. And what this is essentially the reference audio. Instead of just going through the little embedding to make the speaker embedding here, we're actually also using its text tokens, the transcript of the reference, and we're using the speech tokens of the reference to kind of extend, treat it as part of the text synthesis problem that we've already sampled. So now all our text inputs looks like the text of the reference plus the text that we actually want to synthesize. And then our speech outputs, we actually know the first however many speech outputs that are from the reference audio. And then only after the last speech output do we actually, sample the next thing to get the first output corresponding to the text we want to actually say. And then we keep sampling this until we get to the end. So, your main benefit here is that your model actually has better idea of what the reference prosody and what the reference actually sounds like, and what the actual tone of the reference is in its speech codes. So it can better mimic that when we continue the text synthesis to produce the text we want to say. Of course, the main downside here is that your input sequence length is now longer. So it's going to take longer, with the quadratic memory requirements of the compute requirements of the transformer. This is going to take longer. So this is the deep clone where it takes a bit longer, but the model has a better idea of these tokens here, so it can actually do a bit better of a clone. Of course, if the speech of your reference, if you feed in a reference that is very strange, like a very weird scream or gurgle or some audio that the model hasn't really seen much during training and will struggle with, then deep clone might actually do worse, because now you're feeding in a bunch of tokens that it's never seen before. Whereas with a shallow clone, at most your embedding might be slightly wonky, but it wouldn't mess it up too much. But here, it's going to start seeing a bunch of very strange speech codes, and the transcript of a gurgling sound isn't exactly clear, so the model's going to get a bit confused there, especially if it hasn't seen it during training. So I guess this leads us to some of the problems or current opportunities for improving models that we're still looking at. And as we say here, is that when you have a very hard reference, it doesn't clone it super well. This deep clone freaks out a bit, and the shallow clone doesn't yet produce very good implicit embeddings for very hard audio references. And the other thing is that we don't yet have a great way to do long form inference that's actually perfect. This is a problem that I've seen with quite a few of these large autoregressive language models, that it's not exactly clear how to ensure that the prosody flows very nicely, if you feed in a full page of text. How to make sure that, it doesn't sound like you're performing a bunch of TTS in lines in isolation. But probably the biggest problem we've had so far, that I'm sure if you've tried it out, you've seen, is that it's not super stable. So how to sample actually from these autoregressive TTS models is not entirely clear. And by stability, I mean in the actual words being said, not in the actual high fidelity quality. So, if we go back to the whole pipeline, right? We feed it through the autoregressive model. It produces coarse features. These are responsible for exactly the words being said and the actual sounds being spoken. Whereas the non-autoregressive, the diffusion model, is responsible for making a very coarse, low fidelity audio sound like high fidelity, um, audio that sounds like the right speaker. So problems with stability arise actually in the autoregressive model, since it is responsible for actually, including a sound or not including a sound, or including the wrong sound in the actual speech features that ultimately will get improved in quality. So that is the biggest problem that we're looking to address right now. Then also that comes along with these models is that what the best output settings are not super apparent. So for these, auto-regressive models, you've got lots of different features that you can tune. Temperature, top P, top K, repetition penalties, various kinds of penalties on like sequence length. So it's not exactly clear what is the best way to do that. And doing a proper ablation with all these different inference settings on TTS models is probably important to finding what the best settings are for these kind of models. And the other thing that we're not doing super well yet is the DDPM sampling is still naive. So I don't know if any of you guys have played with Stable Diffusion or other AI image generators, but often if you in the inference settings, you'll see they offer this sampler option, which has a bunch of different ways that you can actually sample from the model. You might have heard of Euler sampling or DDPM, or what do they call it, DPM plus plus 2M. There's various kinds of sampling. And at the moment, since this is a fairly different way of doing diffusion, not many people do it this way. There's discrete, diffusion on discrete tokens instead of continuous things. Um, we haven't yet actually added these different diffusion samplers, and they probably will help quite a lot. But yeah, I guess this is where we start to move into more of the community aspect, where if you guys have any contributions or ideas on how to improve it, improve Mars, or general ideas to how to make it better next time, or how to fine tune it to improve some of these things, then any contributions are very welcome. But yeah, I think that's about everything I have to say. So thank you very much for listening. Um, and yeah, I guess if you have any questions, I guess we can start the AMA. Thank you.
Excellent. And thank you so much again. Do we want to have the team come up on stage?
Yeah, sure. Peter Arnold, if you could come on stage, maybe you can add them.
And then while we're getting that sorted, if anyone has any questions, they're welcome to pop on stage or drop something in the chat.
Yeah, go for it.
I have one. It'll kind of make us zoom out a little bit if that's okay. But
Yeah. Sorry, go for it. I realized some of it here might have been a bit in the weeds
uh,
of things.
yeah, I was curious about like what kind of interesting use cases have you seen already out the gates, and yeah, if you could just speak to more of like where does this like having this ability to have better control over the stress and intonation of the speech and the punctuation, like where does this really shine in your view?
Yeah, so I mean, ultimately, what we're trying to do at Camb, one of the core things we're trying to do is to translate videos or audio visual stuff from one language to another. But actually do the full sort of performance transfer. So, if you have some YouTube video in English and you want to translate it to Spanish or something, you don't really just want to get the speaker identity right, or the translation transcript right. You want to really get the full performance, done. So that includes, getting the translation right, getting the speaker identity right, but on a line by line level, actually making sure that it matches the tone, the full prosody of exactly how the original was delivered. So I guess that is why, if you look at our design a bit for this, is that the reference can be very short. It can be, as little, we trained it with about as little as 1 second of reference audio. So, I mean, it doesn't do the best when it has such little reference to go on. Even a human will struggle to make a good speaker impression if they've only heard 1 second of someone. But, it's compared to other models, we think it's quite robust to very short speaker references. And this allows it to essentially have prosody that's more, or the idea is that it has prosody that's more attuned on a small individual, very fine line by line, um, a line by line focus. So between two different lines of the same speaker, the output audio can actually sound quite radically different, just because we actually have two different inputs to the model. Um, yeah, so I guess the idea is that we want to improve this kind of ability to do this translation and dubbing by better capturing the prosody of a reference.
Great. And I see ACT just dropped some subjective comparisons against EL and Meta Voice in our samples demo. Can you talk about that a little more?
Yeah, sure. I think I can bring it up on stage. Let's see if I can do that. Yeah, but I mean, essentially, we haven't had time to do, a full, academic comparison with proper benchmarks. We do hope to get to that at some point. But if you go, here's the demo on the GitHub repo, and you can see several different samples. And the key thing here, if we listen to one of these, so for example, here's the reference audio.
I'm so sick of it.
I don't know if you could hear that, but they said, "I'm so sick of it," in like a kind of a crying tone. But the key thing is it's only 2 seconds, 2 seconds of reference. And now, 11 Labs, they recommend, at least dozens of seconds of reference. And Meta Voice, I think you also have to have at least 30 seconds of reference. So if you try different ways of feeding this into these models, 11 Labs sounds like
I
this.
just can't anymore.
We want to produce the text, I just can't anymore. But I mean, it kind of captured the speaker, but the prosody is kind of lost. It's not, it doesn't sound like that at all. And I mean, Meta Voice really struggles with such short references. It does really well, actually, if you have proper references. But if you have very short references like this, it often struggles quite a lot. But then, with our model, again, it's not super stable. So sometimes it doesn't output good things. But, one thing it can output is this. So it actually does get the prosody much closer, even though it's a bit more echoey. You can kind of hear some of the artifacts, like the vocoder artifacts there, but the prosody is much more aligned with what this speaker's saying. Yeah, and there's a bunch of different samples down here, and if you guys want, you can play with some of the you can try out upload your own sample here. And yeah, it can make a bunch of different audio things. Feel free to play around with these. Yeah, one thing that is quite weird, I see in the chat is that often it does make breathing sounds before it starts speaking. We think this is actually a artifact of a lot of our data. I mean, a lot of these actually have like weird breathing sounds, like just before the speech actually starts. So like here, you can see it kind of breathes in. So here's the reference.
You should not be here.
That's the reference, and then here's the output.
You should speak.
But here at the beginning, it actually does breathe in a bit. So it does do some weird things sometimes. And here also it takes a breath, waits a while, and then speaks. But yeah, it does some interesting things. As I said, these autoregressive models are with Persian voice. Actually, no. Yeah, I'm not actually sure. We haven't tried it with Persian. You could try. You could just this is the public URL in the chat. Then just go ahead and try it. But I mean, ultimately, we are working on making it support, all possible languages. So, if it doesn't work now, it will work pretty soon on it. Arnav, Peter, have you been able to get on stage? Hello.
Hello, I'm Peter. Oh wow, that was rocket science. I didn't know that the hand there meant to come up on stage. We've never used a stage before, I think. But yeah, great to be here, everyone. I'm Akshat. Nice to meet you. Just on the Persian thing, I guess just to give more context, you can actually sign up on our portal today to try out all possible languages. If you have a Persian reference and you try to do it in other languages, it should work well. The open source release is just in English though. So you can try it. I think on the community GitHub, folks have tried references like Spanish references and stuff. People have even tried to generate like Spanish, although the model's not meant to do that in the open source release.
Yeah, and I mean,
And
if you
it
look at
kind of works, I think.
Yeah, I mean, if you look at the model design, you don't want to be using deep clone with, if you suspect these text tokens are, not going to be very representative of what this English only model has seen during training, you don't want to be using a deep clone. So if you're cloning from like Spanish or Persian, these text, the text transcript of your reference is going to be in Persian, and the model's not going to understand that because it's English only. So if this is in Persian, you probably want to use a shallow clone where the model is not being exposed to Persian text, and it'll probably end up doing a lot better if you use Persian reference in a shallow clone setting.
Yep, you can. It's right on the GitHub. I don't think have we left a comment to make it obvious to people how to switch between shallow and deep clone? I assume so.
Yeah, it's in the
Collab?
the Colab notebook, and also here there's just the checkbox for deep clone or not deep clone.
And just for the
I'd
listeners,
recommend playing around with.
yeah, sorry, just for the listeners, the question was, can we change to shallow clone on Camb.ai? Jump in there.
Yeah,
Thanks.
you can. Both on the demo, I think, as Matt is showing right here. I think, Matt, if you just scroll down, it's right at the end, right? Yeah, there you go. So you can go on and off with shallow or deep clone, and then even the collab notebook, which I guess maybe some of you guys are going to try out, you can choose to use shallow or deep.
Yeah, and if you look in the documentation for the on the GitHub repo, you can see an explanation of what each of these settings do and what good settings for all of them are. The defaults are here are pretty good in most cases, but I mean, if you're using like something weird, like doing a Persian clone, you might just want to go to the GitHub and read what exactly all of these arguments do exactly. Maybe you need to tune it and toggle this off, and maybe you need to decrease the temperature. But I mean, you can feel free to play around with it.
Yeah, and with this initial release, of course, there's gonna be more checkpoints and more improvements to the community. I think one thing we guarantee is that like when Mars does well, it does really, really well. Like there are things you can do with it that you just cannot with other text to speech models today. Anything from shouting to crying to, just very tough prosodic scenarios, even when the reference length is very tiny. Um, so I think like if you get the intention of this is like a very initial release. Of course, we've gotten tremendous love and support from the community, and I think it's only a matter of time when you can kind of use this just the open source release, right? Not even our paid platform or anything, just the open source release in something like English as well or better than you can use most closed source solutions, which you have to pay like a lot for. And hopefully that means that the community itself can do a bunch of other stuff with it as well. Because I think you guys know that there's not a lot of really, really good open source text to speech models. And we hope that this one is just, actually usable in production systems right off the bat. Um, there's some other question as well, I think. Can we run Mars 5 locally on a Raspberry Pi? No, not anytime soon, I don't think. Uh,
I don't think there's
but
anything fundamentally preventing it.
yeah,
You can run it on a CPU. Because Raspberry Pi doesn't have a GPU. I know you can buy those NVIDIA Jetson hats for it. So on the CPU, probably yes, it might need some tweaking. On the GPU, I don't know how those Jetson Nano things work, but I think if you fiddle hard enough, you probably could get it to run.
would it, Matt, today, would it fit in size on the Raspberry Pi? No, right?
Raspberry Pi 5 is pretty good. I think the specs on that are pretty decent, and I mean the model's not massive. So if with some proper optimization and fiddling, I think it could. It would be
There
very
you go.
slow, very very slow on a Raspberry 5, but it would work. I think.
Yeah, again, I don't think like I think the intention of creating Mars 5 is it's more it's use case driven, right? And with Camb.ai, like Matt said, our use case is to transform performances from one language to the other. So our stakes aren't very high in even in things like performance, I guess speed performance, so to say, right? That isn't like a major um goal. It is quality and getting quality right first. Um and so I think that's representative of the initial open source release that yeah, you might not be able to run it super fast and stably, but like I said, like when you do get it right, the outputs are actually quite amazing. Um yeah. Future model. I don't think there's a future model that's focused on speed of execution. I think within the next few weeks, the community itself, us ourselves, will have implemented enough that you could use the production systems. And that's the intention. It's not really a success release of Mars. It's more just incremental improvement on some of the, I guess, inference techniques we're doing, etc.
Yeah, and I mean, if you look at the the current way that Mars is, it's more of a just directly released. There's instead of a new model, there's actually a lot of things that can be done to optimize the current one, just in terms of inference speed. Because ultimately, the Aeon model is 700-ish million parameters. The Narn model is about 450 million parameters. That's not massive. You can optimize, if you do proper compilation and quantization, there's actually a lot that can be done with the current model to make it pretty quick.
And yeah, that's where we're hoping, right? We're a small team. Of course, we're a Firepack team, but some contributions will come. The intention of open sourcing was this to also for us to learn where this can go and how far it can go. So we're already seeing some like PRs from non-Camb.ai members, and I think Matt will put up a list very soon of all future roadmap items we want to do, and I guess like to a certain degree suggest what approaches to do to complete those. So we'll just be leaving it out there. When we get time, we're gonna, but when other people get time, they can take it up and quite easily implement some of those things. So we really hope that this becomes a community project. Because I guess that's the point of open sourcing it, that we can grow with the community.
Hi, McMahon. At the moment, you can, but you have to do a little bit of fiddling. So you probably have to clone the repo locally, download the checkpoints locally, and then instantiate the Mars5 object, like in a notebook or something. But we are working on getting a safe tensors release through Hugging Face at some point. So that should happen pretty soon if you prefer Hugging Face. But at the moment, torch.hub.load is the main way. But you can download the checkpoints directly from the releases tab on GitHub if you prefer that.
Well, great. Are there any more questions? Again, really appreciate the team coming in. Please do come back and let us know how things are going. Come back with any updates. This is a really interesting project. And yeah, we thank you again for coming in.
Yeah, thanks for having us. It was great.
Yeah,
Yep,
thanks
thank
for
you.
having us.
Cool. I guess we'll head out then.
Thanks very much.
Cheers, everyone.